Okay? First off, this IPCS shows you lots of information. It shows you if there's a message queue that's been created, how many messages are in it, how much space is being used. Okay? It's extremely valuable if you've got yourself a reader who's created a queue, you'll see it immediately. If there's lots of messages in the backlog, haven't been processed yet, you're going to see them immediately. Okay? Also, shared memory. When the creator launches a shared memory space, a segment, it will show up in here. Presumably, you're going to attach to it, so there's going to be a 1. Okay, a 1. And then you're going to see its permissions, whatever you set up, whether this is read, write for the user, nothing for the group, nothing for other. But I've set mine up so it's read, write, rewrite, rewrite, and the same for my message queue. When the corruptor attaches, the number will go up to 2. The corruptor has to attach. Okay, now I know I'm jumping all over. I'm assuming you've read a little bit about the document, but we can go slow. Okay, there's 3, say, programs, so 3 processes that you're writing. Let's do them in order. Let's talk about the creator first. The creator makes messages. So what does it do first? It turns itself on. Okay? It's going to ask, hey, is there a message queue that's alive right now? If it isn't alive, it will go to sleep and check again. Okay? It checks once every 10 seconds until the message queue comes on. It does not have an upper limit of how long it checks. Okay? So if you mess up for any reason and you want to kill it, you'll find it by typing PS. Okay? In here. And you're going to see a command probably called DC, and then you can find this PID and you can kill it. You go to kill -9. So I showed you this a long, long time ago, and you put in the process ID and you can remove it off the process list. Okay? I don't have one to kill at this moment. Okay, so then it keeps checking, Eventually a message queue comes up. Don't worry about where it comes from yet. A message queue comes up, it finds it, it detects that it's there. It now knows that it's allowed to do whatever it's supposed to do. So what does it do? It goes into its main portion of its program. The very first thing it does is it puts into the message queue a message that says, everything is okay. Okay? I am now alive, you can see me, everything is okay. So it does that first. Then it goes to sleep for a random number between 10 and 30 seconds. So it can be 10 or it could go all the way up to 30. Okay, there's 21 numbers to roll. And then once it goes to sleep for that amount of time, it wakes up, it sends a message. And it's randomly rolled between 1 and 6. So you're rolling a dice. Okay? You roll a value between 1 and 6, you put it into the message queue, you go back to sleep. You wake up, you send another number between 1 and 6, you go back to sleep. You keep doing this until the number you rolled is a 6. The 6 tells you that you're done. So you send the 6, you leave. The DC will just exit. Okay? Basically, it will return and stop. Okay, so that's what the DC does, the data creator. When it starts, it checks for a message queue. If the message queue doesn't exist, it waits. Once it finds it, it will send the very first message which says, hi, I'm alive. Then it goes to sleep for 10 to 30 seconds. When it wakes up, it rolls a dice between 1 and 6, sends that message. If it's a 6, it will send the message and then stop. If it's a 1 to 5, it will send the message and then go back to sleep and then repeat. Okay? That's the data creator. It's nice and short. Okay? The reader is the person who consumes from the message queue. So what does the reader do? There's a couple of things. The very first thing the data reader should do, there's 3 things at first. It needs to open up a log file. Okay? It needs to open up a log file because that's where it stores all of its log messages. It needs to create a message queue, and it needs to create a shared memory segment. Okay? The order I did it was shared memory segment, then message queue, then log file. I have a reason for that. Okay? It's definitely easier turning on the shared memory and then the message queue. Okay? Because you're actually supposed to store the queue ID in your shared memory. So it makes sense to have this guy already up and going. He already has space. Then when you create this guy, then you move that value in. Okay? If you do it the other way around, you're going to have this temporary variable holding on to the queue ID until the shared memory comes up. So I did it the other way around. Shared memory ID, shared memory segment first, and then a message queue. Take that queue and store it. Okay, that's one. I also did my log file third. Why? Because opening files is very, very expensive. Okay? If I open up a log file and then either one of these things fail, now I'm responsible for closing down the file, and it's expensive to open it. So I should try to ensure that both of these guys work before opening the log file. If neither of them work, well, the program will eventually terminate, so I don't have to open the log file. Okay? The log file being the most expensive should be the last thing you do. It should be contingent on the other stuff being successful. Okay? Does that make sense? Right? So that's the order I did it. That's my reasoning. You don't have to do it that way. I'm not going to grade you that you did it out of order. It doesn't matter. But I'm telling you how I did it. So there's a first phase. Data reader comes online. It runs its main. It opens up those three things. Queue, shared memory, log file. Then what does it do? It goes into the message queue, starts pulling messages. First in, first out. Okay, there is no selecting here. Just take anything that comes, first in, first out. Every time you receive a message, process it. And then go to sleep for 1.5 seconds, wake up, take the very next message off the queue, and then go back to sleep for 1.5 seconds. Take the message off the queue, go to sleep for 1.5 seconds. Okay? And you repeat that over and over until something special happens. Okay? The only other thing that I have to say is, right after you grab a message off the queue, you should go and check to see if there are no more machines, no more data creators. If the number of data creators ever drops to 0 at that point, you should just stop. Okay? So now let's revise our loop here. I've already turned on all three things. The loop I said was to read a message, process it, go to sleep. Now it's read a message, process the message, check to see if you're in a case where there's no more machines, no more data creators. If so, stop. If not, go to sleep. And then repeat these 4 things. Okay? And then once you are done this loop, meaning there's no more machines connected, which is the step 3, and you're leaving, close down all 3 things again. Close down your log file, close down your shared memory, close down your message queue, and that's the end of the program. Okay? What about the message handling? The message handling depends on a few different things, okay? At its most simplest, if you do nothing advanced, all you're gonna do is this. If a machine sends you a hi, everything is okay message, which was the 0, the very first message it was supposed to send you, you add it to your master list. This is now a machine you've never seen before. Okay? It goes into your collection of machines, my list of machine names. If it's a 1 to 5, meaning it's not the death message, any other number, 1 to 5, you just record it. And you say, I know I've seen you before because it's not a 0, it's not the everything is okay message, it's a 1 to 5. Let me write down these messages. 0, 1, 2, 3, 4, 5, and 6. This guy says, this is basically your hello handshake, your hi from client. This is the goodbye from client. And these are just random values. Doesn't even matter. Random status. They mean nothing. Okay? So, remember, the client comes on. This was the data creator. It comes online, checks for the message queue. If it finds it, it sends you a hi from the client. That's its very first message. After that, it rolls a 1 to 6. If it's a 1 to 5, it doesn't matter what it is, send it, go to sleep. Wake up, send it, go to sleep. Once you hit the 6 and there's a goodbye, you stop. That's what the data creator does. Nice and easy. The data reader reads from the message queue. The very first thing I should see from a machine is a 0, meaning I've never seen you before. I add you to my list. I write you down on a piece of paper. I've now seen you for the very first time, and I write down the time that I saw you. I keep reading from the list. If I see a 1 to 5, I go and edit my list, and I say, hey, I know I've seen you before. I go back to the list, I check your time, and I update your time to the new time, to the time I received it. If it's a 6, it's a goodbye. Okay, I assume that you're going away for the time being. Okay, goodbye, and I just remove you from my list. Okay? That's how you handle these messages. So you do the following. I grab a message from the queue. If it's a 0, I add you to my list. If it's a 1 to 5, I update my list. If it's a 6, I remove you from my list. After I handle that message, I go back through my master list. How many people are still around? If everybody has said goodbye, if everyone has said goodbye, I stop. Okay? And then there's one final thing in there, which is how do you know if everybody is gone? Well, either they've all said goodbye. If any machine, if you haven't heard from at least, or any of the machines, or from a given machine, I have, let's say I've got 7 machines, and machine number 2 hasn't been heard from for 35 seconds, I presume that they're gone. Okay? They've somehow terminated, their process has ended, so I will disconnect them manually. Okay? They don't have to send me a 6, I just assume that they haven't talked to me. It is a 6. Okay? Like basically, they've said goodbye. Okay? So let's just look at those 2 first off. Okay? So I'm going to show you my, my structure here. The only things that you need to have to hand in are these, up to here. This is required in your submission. You're required to put a top-level makefile. You're required to have a data creator, data reader, data corruptor with its internal structure, with their makefiles. You are required to have a common directory where all the executables get copied into its bin. Okay? I made 2 others. I made one called message queue killer and shared memory killer. Why? Because there will be times when, as you're developing and you're trying to test things, that you may have to manually kill the reader. And if that happens, or it drops for any reason, the shared memory may still be up, the message queue may still be up, and then you can't run your data reader anymore. Okay? So you could either go into the IPCS, into here, and just find the process, and then kill it, like find this ID and kill it, or you can do like I did and run one more program to actually manually kill them. Okay? This one kills the message queue, this one kills the shared memory segment. Okay? You don't have to do those, but very, very useful. Go ahead. Correct. You will have them in here, one here, one here, one here, and then copies go into here. Okay? Go ahead.
So what's the top make file for it?
This makefile,
We need that one?
this makefile is required, compiles this, 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 and this.
So there's, I thought there's 3, so what's the common?
This common, if you have any functions that are common to anything else, then you don't have to reproduce them inside the reader and inside the corruptor, for example. You can move them into a source file in common, and then compile that into an object file.
That's required?
If you have, it's not part of the requirement, if you have anything that's reusable, okay? For example, I have functions that are used by the message queue killer and the creator, the reader and the corruptor. I also have functions that are used by the corruptor and the reader, and I also have another function that's used by the shared memory killer, the reader, and the corruptor. Lots of things are in common. Here, I'll show you. Okay, let me just show you. These are all the things that I thought were common. Okay, get shared memory key. Attach the shared memory. This one's used by the corruptor and the reader. This one's used by my shared memory killer, reader, and corruptor. This one's used by corruptor, reader, message queue killer. Open log file is used by the corruptor and the reader. Log is done by the corruptor and reader, and close log file is corruptor and reader. So they're common. They're exactly the same. There's nothing in them that is any different, so I move them out. Rather than reproducing them twice, I put them in one place. Okay? Are you supposed to? Well, that's the whole point of this common folder, right? So if you look at that document where it says setting up a Linux project directory, that PDF, it shows a picture. And then beside the common blob, it says, what are you supposed to put in the comment? It tells you anything that's reproduced in multiple projects, put them here. So I did that, right? Just to follow along. Okay, I'm going to make it now. Make. Okay, so it made them all one by one. And then on top of that, I have to move everything in. So if I look inside my common now, there's nothing in there. So I'm going to install, and then everything will go in now, for example. Okay, so now I've got all these. I'm going to show you what I'm going to do now. Common bin data reader. Remember the ampersand. If you don't do the ampersand, it locks the terminal. Okay, I can't type anything. It doesn't actually do anything. Okay, so I can't make a reader. It doesn't do anything. So I can close this, but now we have a big problem because I sent it a term, like a kill signal, and I still have this shared memory and this queue. That's just being blocked. If I try to run the reader again, now with the ampersand or even without, it's going to fail. Shared memory already created. Well, I don't know what to do. You could, if you wanted to, kill it from here. You know it's shared memory ID, so you can actually go IPCRM, okay, and remove this guy, or you could be lazy like me and just go like this, bin shared memory killer, okay, that kills this 1540109, which is the same as this guy, and I'll also kill. Well, I'll kill this. I don't know if I actually printed it. So this is my message queue killer. Okay, message queue ID was a 0, I suppose. But if I IPCS now, IPC show, it's gone. That's gone, and this guy is gone. Okay. All right. So let's do this properly. Let's run it with the ampersand, so I don't lock my own terminal. 1. Then I'm gonna go creator. 1. I'm going to go 6. There's a reason why I'm doing it slow. Okay, I'll show you what happens when you do it fast after. Now if you take a look in the temp data model, okay? So you can see that I added 6 of them to the master list. Each one sent to 0. This guy subsequently sent. So there's something wrong. I'm going to have to remake it maybe. Something is wrong with the RAM. Okay, so I'm going to have to clean and remake. It looks like one of my directives, my pound define, isn't working. Because this is only 6 seconds and it shouldn't have happened. Okay? And then this is only 6 seconds, so that shouldn't have happened. Anyways, let's continue. So more messages are being sent, more messages. So what am I seeing? Here, let's just make it smaller. Oh, let's make it smaller again. I wanted to fit on one screen. Okay, that looks good. So I've got a bunch of things happening. Every time this guy, or any one of these guys sends a 1 to 5, which is what you can see here, I just update their time. If they send a 0, I actually add them to the master list. If they send a 6, I remove them from the master list. So now that 10994, take a look at 10994, was a DC04. Now that it's been removed, the DC05, which is a 10995, needs to move to a DC04. DC06 needs to move up to a DC05, so it collapses. But 2 of them go off at the same time, so now it has to collapse twice. So 3 and 4 have gaps now, so what used to be a 5, which is a 10995, shows up as a 3. 1 doesn't move, 2 doesn't move, 1 doesn't move, but 4, which used to be, I guess, a 6, 10997 used to be 6, now moves down to 4. Okay? This continues going until everything is dead. 3 have gone offline. Now you can actually see them if you PS from here. Okay? 3 of them have disappeared, those 3. 3 more to go, 1 more data reader to go. Okay? If you check the IPCS now, you can still see that this is my queue. Nothing is in here because it's reading really fast. 2 things, no, 1 thing is attached to this shared memory because I don't have the corruptor yet. It's only the reader that's using the shared memory at the moment. Okay? Let's see if I can spot a message coming in. Nothing yet? Here, let's speed this up. Data, here, let's do this. Let's make more and we're going to see the messages pile up. Okay? Messages are piling up. But it's fast. It's reading so fast. I can't keep up. If we look in the main now, not in the main, in this log, we're going to see a bunch of people being added. Okay, these people are being added. Now, I did something that's not in the spec. Okay, notice here I added so many new DCs that I hit my upper limit. This isn't actually specified anywhere in your document, but I keep track of how many you're supposed to have, and then I handle it this way. It doesn't say how you're supposed to handle it, you're just not supposed to have more. What I did was I printed out the new process, which is 11028, 11029, and I said, hey, I know you're talking to me, I just can't add you. Try again later. Now there is something else that's going to happen. Now that this DC01 has gone offline, it makes room. Okay, it makes room. So now what's going to happen is the next time somebody sends a message, I will add them. Okay, but it won't be added as a status 0. I'm not testing on the 0. Okay, so up till now I've kind of been saying, well, if it's a 0, it's new, add them. If it's a 1 to 5, we'll update them, and a 6, kill them. That's not what I do. Okay, I do this in a different way because it's actually more extendable. Okay, I don't assume 0 will be your very first message, because if you mess up and send 2 zeros, well then I may add you by accident if I'm depending on the status. Okay, what if you send a 6 and then a 6? I removed you, now I'm supposed to remove you again. That gets dangerous. So I don't actually do that. Okay? Let's just see what I do. So, take a look. Remember how we had too many people? Too many people? Well, 4 of them just went offline. I added people to the master list, but they came in with the status 3. 11028, first off sent a 0, and I couldn't add them. Then next time they rolled a number, they sent me a 3. I added them. Okay, I wrote new DC and I added them under this status. 11029 made room because a bunch of them dropped. So I made room for that guy. And let's see if there's any more. Offline, offline. Okay. This is why I was saying I was spacing them out. Take a look at this. It doesn't look random. 4, 4, 4, 4, 5, 5, 5, 5, you know, a bunch of 3s, a bunch of 5s, a bunch of 2s, a bunch of 3s. Remember I told you, computers don't do random. There's no such thing as randomness, typically, in a program. Okay, you can't actually enforce randomness. You have to have some random event. Computers don't do that. I made it so fast that I started them all at the same time that they all have the same seed. The seed is the time from epoch, basically time 0. Okay? They all had the same time because I started them all identically at the same time. They all start in the exact same place on the random list. If 3 or 4 people start on the same list and they use this number, the very next number is already known. And they're all taking that step together. Okay? So it's not random. They all sleep for the exact period of time. They all choose the exact same role. Okay? So take a look, for example. 1, 2, 3, 4, 5, and 6. Okay? All 4. 2, 3, 4, 5, 6, all 5. Let's check them out. 2, 3, 4, 5, 6, all 5. 2, 3, 4, 5, 6, all 3. It's not random. Okay? That's because I went up, pum, 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 and I started them all at the same time. Okay? So that's why I was slowing it down. Let's just check real quick. Let's see. A bunch of people are gone. I still have this guy up. Let's see how many people are still around. I still have 4. I might just kill them. Killing them is this. Now that I know what they are, go ahead and kill them. I'll kill the DR. Okay, dead. Now that that's dead, the DCs will still try to send because it doesn't know the queue is down because the queue is not down. Okay, the queue is not down. They're still sending messages. The shared memory, they don't even know what it is, but the queue isn't down, so they're not down either. What I can do is I can kill that queue, which is what this guy was designed for. Now that this happens, all the creators will die too. Okay? They should all die once they come up and they see that they can't send messages. The other thing I want to do is, now that I'm waiting, see, there they are. They're all dying. Okay? There were 4. One of them, nope, that's 4. That's 4. They're all dead now. Okay? Yes. They're all dead. Okay, the other thing I want to do now is also kill the message, no, the shared memory. Okay, the only thing you haven't seen now is what happens with the corruptor. The corruptor is trying to mess things up. So I explained the creator, I explained the reader. There is a corruptor. The corruptor does the following. It comes online. It looks for the shared memory, not the message queue. Not the message queue. It looks for the shared memory. It's looking for the one that was down here. If it can find it, it will attach. If it can't find it, it goes to sleep. It does that for 100 times. Okay? It tries to attach to it 100 times. If it can't, it just fails and stops. So if I turn on the data corruptor without the data reader, it will just continue checking. For example, it shouldn't do anything. It just sits there and doing. And if we want to see it, we can actually see it from here, of course. We see it. It's running here, but it's not actually attaching to anything because it's not in charge of making anything. Okay? It will eventually. It has to do the following. Attach to the shared memory, make a log file, okay? Now, because opening a log file is the most expensive thing you can do, I actually do that second. I make it contingent. Don't open the log file if the shared memory never comes online. What's the point of opening your log file if you're just going to close it after? Okay, so I do the other way. I check for shared memory. If it exists, then I open the log file, then we're in business. Once we're in business, what do? We roll a dice from 0 to 20, so 21 different options. Depending on the option, you can do one of the following. You do nothing. Okay, so that means just go to sleep for 10 seconds and then come back online and do something else. The other things I can do, it can close down your message queue prematurely. So it can actually go in and close it down. And you saw what happens when it does. All your creators and your reader needs to die. They all will die. Okay, handle that gracefully. Don't allow them to continue doing whatever. Okay, handle it. And then the other thing that it can do is it can go through the master list. There's 10 data creators. It will randomly select one, maybe, and then kill it. Send it a kill signal. If it kills, that thing should stop sending messages. Eventually, the data reader will sense, wait a second, that guy hasn't sent a message in a long time. What I still need to do is the following. I need to actually into my comment. I need to, I gotta get this thing. It went too fast, and I can tell that it's going too fast. So that's not, it's these. Okay, let me try this again. So the data creator, the corruptor, will mess things up. You have to be able to handle it. Now, I wrote a script so that I don't have to manually press up, up, up. And hopefully you can follow the script. It's very easy. Run the reader with an ampersand so you don't lock yourself out. 15 times. You don't have to do 15. You can go 10, you can go 6, it doesn't matter. I made creators 6 times. Why? Because I wanted to see the ability of overloading my reader. There will automatically be 5 creators, up to 5 creators that are sending messages that keep polluting the queue. If they pollute the queue, it's very likely that the reader who's looking says, hey, I'm checking for this 35-second time window. People may not get their messages in time. Okay, because let's say there's 15 of us and I was the first one to send a message. Okay, you guys throw in a bunch more messages inside, I send in one more. It is possible for the reader to try to reach me, just not get to me in time. Because there's 15 more messages between my first message and my next message. At which point the reader needs to turn you off. Okay, basically pretend you're not there. Then what happens? Now that I send another message, and this time it won't be a 0, it might be a 2, okay? What does your reader do next? Does it add you to the list or does it not accept you? So I made it so it would add me back into the list. Okay? So I have here 15 and then I turn on my corruptor. So this is what I'm going to do. Okay? Wait. Common bin DC. DC is not there. Oh yeah, because I didn't install. I cleaned but I didn't install. can even tab off this guy. If I press 8, I can tab off. There's more. Okay, let's check again. I'm gonna have to kill the message queue, shared memory. Okay. Okay, let's try again. Okay, so now in here, there's a bunch of things I can do. I can check to see if the data corruptor log is here. Okay, so that means the data corruptor has found the message, the shared memory, and is up and running. There's also a data reader. I don't remember what it's called. Monitor. Okay, it has currently added 8. Okay, let's see how many more can go. Yes, there's a bunch of messages waiting to be read. Okay, this guy's already gone offline, and somebody also went offline, but he wasn't even added to the master list, so I'm not going to put him on. I just note that he's gone offline and sent it to me. Is there anything else to read from here? Any questions? I know I'm jumping all over and I'm showing weird things, okay? But if you have started a little bit or have read the document over and over, you can try to see some of the details, okay, that I'm trying to highlight, and we can talk about it. Okay? Let's see if the corruptor has done anything weird yet. Oh, he's killed 3 of them, okay? He's killed 11304, 308, and 312. So eventually, the reader will notice that they're not sending. 304, 308 was here, so that's a DCO2. So DCO2 should eventually send a non-responsive. Let's see, 35 seconds would be 39. So it's got, oh, it's right here. Here it is, non-responsive. That's the 304 and the 308 non-responsive. Okay, so that corresponds to 2 of them. I've killed 3 though. There should be 1 more coming. Non-responsive, non-responsive, non-responsive. Okay, let's check the corruptor again. He's killed 2 more. Okay, there'll be a 11335 and a 11310. This guy eventually will come back with a non-responsive within the next 35 seconds or so. I'm waiting for the corruptor to kill the queue though. That's what I would like. So if it doesn't happen, I'll just run it again. Any questions? Come on. Okay, there's one of them. Both of them. Okay. They're all the non-responsives are handled. Any questions? Yes, go ahead.
So what would the process be as soon as the message for killing a process? Like the thing that gives you the random numbers and decides to kill a process sends the message.
Yeah.
It's received by the reader, and then what does it do exactly?
If I'm going to kill a process, send it to the process.
Okay.
Kill, send the process ID, send the signal. It's running this command directly to the process, 11310. So it looks like this. In your case, you have to send this. They tell you. That's signal hang up. So it's pound defined to be a 1. But don't write it as a 1. Write it as the actual variable, which is called sig up. So signal hang up. So send the signal to this process. The actual reader doesn't know. The reader won't sense it until he realizes 35 seconds from now, I still haven't heard from this guy. I guess he's gone. And then I write it down as non-responsive. Okay? It's actually backwards. You don't want the corruptor to directly talk to the reader. It's meant to be like an intruder process where you don't really know what's happening. Okay? You kind of figure it out based on the fact that nobody's talked to you yet. I want to see this corruptor. Okay, it's still hanging around. There's a reader and a corruptor. The reader is going to go down very soon because there are no more creators. Okay, currently the reader thinks it has one more person, it's going to notice that that person has gone non-responsive, everybody has gone offline, it will turn itself off. Okay, I can tell that because right now there's only a reader and a corruptor. It's going to notice that somebody's gone non-responsive, therefore its master list is empty, therefore it will shut down. So we might as well just wait here. Okay. Next 30 seconds. Alright. Come on. 11108. It's gotta know this now. What's happening? Ah, here we go. Oh wait, did I kill the queue too? Let's just check. At the same time, oh, I also killed the queue. This person deleted the queue. There are no more talking, and then the reader, which tries to read a message, can't receive the message, so then it quits and stops itself. And then the corruptor will also turn itself off. Okay? So everything is down. If you check IPCS, everything's off too. Okay? Questions? Is there any portion of the assignment that's holding you guys back at all? Anything we want to talk about? 'Cause it's not easy by any stretch, so I'm willing to talk about it. With the what?
The corruptor.
With the corruptor. Is it the same problem as you were describing before?
I think so, yeah. Yeah.
So describe it to me once again so I can understand the observables.
So, if I have a client that's running,
A creator.
a creator,
Okay.
and then say the corruptor kills it.
Okay, it kills it, yeah.
So right now there's 0 clients.
Yeah. Which the reader doesn't know about until 35 seconds has passed.
Yeah.
Okay.
So the corruptor, say the corruptor tries to kill again,
The corruptor tries to kill again, yeah.
it will just skip it.
Well, it should try.
It will
It should try because it thinks it's alive. It doesn't know. It will think it's alive. Which is perfectly fine. You can send that process a kill signal. What happens if you try to kill a process that's already been killed?
Nothing happens.
That's not true.
Well, it sends an error flag.
It will set the error. That's how you'll know it didn't work. But that's not a problem. Okay, so suppose we get past that. What is the issue here? It failed somehow or what?
So the issue is let's say if I have 0 clients from the beginning,
0 clients from the beginning, yeah.
and I run the corruptor will hang.
It shouldn't. I'm not sure why. The corruptor doesn't care about the creators.
Yeah, that's why.
Are you absolutely sure that your problem is being described by the details you're giving me? Because I don't think it should. Because if it is, then you're doing something that you shouldn't be. You are tying the existence of your corruptor to the existence of a creator, which doesn't happen. The corruptor doesn't care if a creator exists or not. It only cares if the shared memory exists.
Yeah, I'm checking the shared memory. The information
Yeah.
in the shared memory.
Yes, exactly. That's the only way it knows about the creators. So then what happens? So then it finds that it's supposed to kill one. Let's say it's DC01. I read its PID off the shared memory. I send it a kill signal. 10 seconds later, I randomly select it again. Poor guy, I've killed him again. So I'm just beating this dead horse. I send it another kill. This time it returns an error message. Error message? Fine. Deal with it. Move on. It's not a big deal. That shouldn't make the corruptor close. You're saying it's hanging because it's what? It's now doing nothing? Are you absolutely sure it's doing nothing, or does it close?
I have to check.
Okay. All right.